Hello, I'm Dr. Bill Stewart, and welcome to our class today, which will deal with mathematical problem solving. We're going to look at a class of problems that is very popular on standardized tests. It's the type of problem where we take a circle and then we inscribe inside that circle a regular polygon. And then the question usually is, what percentage of the circle's area is covered by the polygon that was inscribed inside the circle? And of course that's going to be some type of percentage less than 100, because the polygon will be somewhat inside, so there'll be some clear area that just belongs to the circle and is not part of the inscribed polygon. So before we get into those problems, I just want to review a little bit of geometry concept. Figures are made up of different symbols, and the first building block in a geometric figure is a point. And a point is nothing more than a dot, and that dot is infinitely small, and therefore we can put an infinite number of those dots in any space. So if I have two dots, 2 points, I can then put as many as I want inside that space between them. So infinitely small, therefore we can have an infinite number of points in a curve or a line. As we make up, as we bring these points together, we can then make up a line or a curve, which is a set of points that can then make up shapes. So we're going to be using a curve, which allows us to draw a circle, and then we're going to be looking at polygons, like an equilateral triangle made up of 3 lines. Okay? So what we're going to do is put a shape like this inside the circle, and then we're going to ask ourselves, there's an area taken up by the equilateral triangle, and then there's area outside here that only belongs to the circle. And so we're going to ask ourselves, what percent is covered by the polygon? So polygon divided by circle. Okay? And we'll use that as our reference for how much space is covered proportionally by the polygon inside the circle. Okay, so I'm going to erase that and we'll start our first problem. Okay, so we're going to start with the simplest polygon. And when I say polygon, we're really talking about regular polygons. Now, what is a regular polygon? A regular polygon is a multi-sided figure, poly meaning many, many-sided figure. And we're going to make sure that each of the segments, the line segments that form the polygon inside the circle, all of those are equal. So there'll be some symmetry going on here, and that symmetry will be important to us as we draw the shapes that we are going to use to do the calculations. Okay? So we're going to start with the equilateral triangle. Okay? So let's start with a circle. And then we'll connect. Like that. Okay? So, the part of symmetry that we'll use on all these calculations is that the center of the circle and the center of the polygon coincide, meaning they're the same point. That's important as we try to work through this problem. And the second thing we will do is we're not going to use numbers for like the radius or for the length of a side. We're going to use symbols. The reason for that is that once we do it in general, then we are assured that for any dimensions, that same percentage will hold. So whenever you have a chance to prove something, it's best to try to do it in general using algebraic symbols so that when you're done, the solution is not specific to a set of dimensions. So that's what we're going to do throughout all this analysis. Okay? So the first thing we're going to do is draw the radius, and we're going to do a very particular radius which connects to the circle and to the vertex of the equilateral triangle. And we're going to label that R for radius, capital R. We're going to do the same thing over here, and that's also going to be R. Okay? And now we have formed a triangle, and I'll use a different color to outline that triangle. And the other thing we'll notice is that if I would draw this there, that we would have another triangle right here and another triangle right here, which those two are exactly the same as this triangle, again through symmetry. Because this is equilateral triangle, all the radii are equal to each other, and each of the sides is equal to each other. Therefore, we have a congruent triangle. So we have three congruent triangles. If we're trying to find the area of the triangle, all we have to do now is focus on one of the triangles, figure out its area, and multiply it by 3 to get the total area, and then compare that to the area of the circle to get our percentage. Okay, so we're going to focus on the green triangle right here. The first thing I want to do is try to get the angles. So we have a circle that's 360 degrees. You can see that we divided that equally in 3 parts. So if we take 360 degrees and we divide that by 3 equal parts, we'll get each of those to be 120 degrees. So this angle right here, this angle right here, this angle right here will all be equal to 120 degrees. All right, now how do we find the area of a triangle? Well, we may recall that the area of a triangle, I'll use that symbol, A sub triangle, is equal to 1/2 the base times the height, where this would be the base and this would be the height. So we'll label this as the base, and that's the height. So if we know what the height is, we know what the base is, we can use this formula to get an expression for the area of that one triangle, multiply it by 3, and that'll be the total area of the equilateral triangle, then compare that to the area of the circle in a ratio, and that'll tell us what percentage is covered by the equilateral triangle. Okay, so how do we deal with this triangle here? Well, it's easier for us if we will focus on 1/2 of that triangle. So I'm going to put black there. Okay. Now, when I drop this altitude or height down to the base, I dropped it in such a way that I formed a right angle there. Now that right angle ensures that when I drop from a point to a line at a right angle, that I'm going to bisect that side. So this side is equal to that side, So I'm going to use little b to indicate 1/2 of that base, because that's what we're going to focus on in this black triangle. All right, so let's see what we have here. The angle we said was 120 degrees. When I bisect that angle, 120 divided by 2 is 60 degrees. So that's 60 degrees. This is 90 degrees. Therefore, this has to be 30 degrees. So we have a 30, 60, 90 triangle with the hypotenuse designated a length, capital R. So let's draw that triangle out here, this black triangle right out here, and label the angles. There's the right angle. Here's our R. This is little b. This is h. This is 30. And this is 60. Now, some of you may remember that this triangle has special relationship among the sides. And I'll draw right over here a standard 30, 60, 90. 30, 60, 90. The ratio of sides for a 30, 60, 90 is 1 to square root of 3. So, any 30, 60, 90 triangle will have the sides in the ratio of the smallest side being 1, the largest side, hypotenuse, being 2, and the intermediate side being the square root of 3. Okay? Now that's helpful to us because now we can relate in ratios what h and b must be compared to r. All right? So let's see if we can do that. Let's say that h is to 1, corresponding part h is to corresponding part 1, as, now we're dealing with this triangle, that would be r is to 2. Okay, so let's do that again. H is to 1 as r is to 2. H is to 1 as r is to 2. H is to 1 as r is to 2. Therefore, solving for h, this implies that h is simply equal to r over 2. Okay? Now, let's look at getting an expression for the base, little b, which is just the black triangle. So, base is to what? Base is to square root of 3 as, base is to square root of 3 as r is to 2. Okay? Do that again. Base is the square root of 3 as r is to 2. Okay? Now let's solve for b. We'll multiply both sides by square root of 3. That'll cancel that out. And so now what we have is that b is equal to square root of 3 over 2 times r. Okay? Okay, now let's find the area of the black triangle. Okay? So the area is going to be 1/2 little b times h. Okay? Now we know what b and h are. So a is going to be 1/2. All right? Now the base is square root of 3 over 2 times r, and h is r over 2. All right? So let's see what this comes to. So square root of 3 r squared on the top, and on the bottom we'll have 2 times 2 times 2 is 8. Okay? Now remember, this is the triangle that is just the black triangle. We want to get the whole triangle here. We see that this green part here is exactly congruent to the black triangle, so all we have to do is multiply this by 2. So what we can say is that the area of the triangle that we're actually going to use in our final calculation is going to be 2 times this figure, which is square root of 3. Oh. 2 times square root of 3 r squared over 8. To get a little different term for that. This will cancel that, so what we have is the square root of 3 r squared. 2 and 8 leaves us with 4. Okay? Now, that is the total green triangle, of which there are 3 to make up the total equilateral triangle. So I can say 3 times this, square root of 3 over 4 r squared, is going to be the area of the equilateral triangle. Equilateral triangle. Okay? Now, how does that compare to the circle? Well, let's form a ratio. So we'll take 3 square root of 3 over 4 r squared, that's the triangle, divided by the circle. Now the area of the circle is going to be pi r squared. Now a nice thing happens here. We have r squared on the top, r squared on the bottom. They will cancel out. And that leaves us on the top 3 square root of 3. We have a 4. And we have a pi. Okay? So that's going to be the number that tells us the portion of the circle that is covered by the equilateral triangle. And if we do that arithmetic on our calculator, that comes up to 0.4135. So if we want to convert that to percentage, which often the answer will be given, we move our decimal place 2 places. So the percentage is going to be 41.35%. So less than half. So the smallest shape, the smallest polygon, 3 sides for an equilateral triangle, will cover just over 41% of the area of the triangle. Okay, we're going to erase the board and come back and do a square. Okay, now we're going to do a square inside the circle. Square is a 4-sided figure, regular polygon, all being equal. Okay, so let's do square. And I might ask you before we start, do you think the square will cover more of the circle than the equilateral triangle? Think about that a second. And we'll find out. Okay, so let's start with the circle. Let's draw a square. The center of the square will coincide with the center of the circle. Now let's draw 2 radii, one down to this vertex, one down to this vertex. Okay? Now, circle has 360 degrees. We're going to divide this in 4 quadrants. So we divide that by 4. So 90 degrees. This angle right here is going to be 90 degrees. Okay? If that's 90 degrees, and this is R and that is R, we have an isosceles triangle where we have R and R. That means these 2 angles are equal, so these will both be 45 degrees. Okay? And that's another one of our popular triangles, which is the 45-45 right. So let me draw that over here. So this is 90 degrees. This is the hypotenuse. And when we have that situation with a 45-45 right, we have the ratio of the sides are 1, 1, square root of 2. Okay? So that's going to help us here because, again, we want to find this side right here. Okay? So this is a 45-45 right, and this is R and that's R, corresponding to 1 and 1. Let's do our ratio and proportion again. Let's call this S for the length of the side of the square. So we're going to say S is the square root of 2, okay, as R is to 1. Solving for S, square root of 2 times R over 1, so just S equals the square root of 2 times R. Okay? Now, if that's S, the area of the square is going to be length times width, or S squared. Well, that's handy, because now we know what S is in terms of R, so the area of the square is going to be this squared, which is square root of 2R quantity squared. When you do that, if you take the square root of 2 times square root of 2, guess what? You get 2, and R times R is R squared. So the area of the square, okay, is going to be 2R squared. I remember back in the triangle we had divided up into 3 different pieces. We did divide this into 4 pieces, but because we can immediately get an expression for S in terms of R, we can go right to the area calculation. We don't have to multiply by 4. That takes care of the whole square. So here we have area of the square is 2R squared. Well, we know what the area of a circle is. So we'll take the area of a square is 2R squared divided by the area of the circle, which is pi R squared. Again, the R squared cancel, and that ratio is going to be 2 divided by pi. And 2 divided by pi gives us a ratio of 0.6366. So on a percentage basis, that's going to be 63.66%. A little less than 2/3. But I asked you before we did this, did you think it would square would cover more than the equilateral triangle did? And indeed, it did, significantly more, from 40% or so up to 63.66. The final calculation that we'll do as practice for this is going to be the octagon. So I'll get the board prepared and we'll do the octagon. Okay, so for our final calculation for this class, we're going to do an octagon. I've taken the circle, I've inscribed an 8-sided figure inside that octagon. The octagon is a very popular shape. It's what our stop signs are. It's also used for all types of other type of signage. And so we're going to approach this in a similar way. We'll work from the top this time. We'll form a triangle like that. And again, this will be R, the radius of the circle, contacting the vertices of the octagon on the circle. We have one baseline across here. All right, so going as we've done in the past, let's find this angle. Well, we have 360 degrees. We're going to divide that by 8, and that'll give us 8 into that goes 45 degrees. Okay? So this angle right here is going to be 45. If I come down and drop a perpendicular, then this angle, it will be half of that, so that's going to be 22.5 degrees. Okay? And let's label our two figures. This will be B, little b, for half the big base, and this will be h for the height. Okay? Now we're going to use a little bit of trigonometry, because this is not a simple triangle that we have memorized. Okay? So we are going to use trigonometry to find the base and the height. So we have a right triangle here, as we've used before. Therefore, we can use sines and cosines. Let's find b. Well, that little base, okay, divided by the hypotenuse, r, is going to be the opposite over hypotenuse, the sine of 22.5 degrees. Therefore, little b is going to be r times sine 22.5 degrees. Now we'll have to calculate this using a calculator. Okay? We don't have those memorized. Let's do the same for h. Well, h divided by r is going to be the adjacent side divided by hypotenuse, and that's the cosine of 22.5 degrees. So therefore h is going to be r times cosine of 22.5 degrees. Okay? Now, the total base is going to be twice this. The height is going to be this. And the area of the total triangle is going to be 1/2 the total base times the height. So area of the triangle is going to be 1/2. Big B, B is twice little b, times the height. Okay, so let's see what that would be. 1/2. If I take this base and multiply by 2, I'll just put a 2 out in front. So I have 2 times r sine of 22.5 degrees. And that'll be for the big B. And then I want the height. That's just this. So that is multiplied by r times cosine of 22.5 degrees. Okay? Now, the 2 will cancel this out. That knocks that out. Now this triangle was this triangle here. We have an 8-sided figure, so there are going to be 8 of those triangles going around there. So now, total triangle, I'll use big, or all the triangles, let's just do it this way. Area of the octagon, which is going to be 8 times this, okay? So I'm going to put an 8 here. The 2's have canceled because of the 1/2. And now I've got r squared. And then I have sine of 22.5 and cosine 22.5 degrees. Okay? So let's just do a few numbers here. Of course, we have the 8 times r squared. Now, we can use our calculator to figure that out. So let's do 22.5, and we'll find the sine of that, which is 0.38, rounded off, 0.3827. Okay, and now we'll do the cosine, 22.5 degrees, cosine 0.9239. 9239. Okay? So we'll multiply these two numbers and multiply by 8. So let's do all that together. So we'll take 8 times 0.3827 times 0.9239, and what I get is 2.8286 r squared. Okay, let's finish the calculation. Area of the octagon is equal to that number there, 2.8286 times r squared. We're sort of used to this now. This will be pi r squared. R squared cancel. And we'll now divide 2.8286 divided by pi. And we get 0.9004. Okay, so percentage-wise, move the decimal place 2 places, will be 90.04%. Okay, so we left out some of the figures in the sequence, so I'm going to write down those percentages as a summary so that if you want to practice a little bit with the other figures, you'll have something to compare your calculations to. So let's, so we'll do the triangle. We had that at 41.35%. We had the square at 63.66%. We didn't do the pentagon. It would have come out to 75.71%. The hexagon, which is a popular shape, especially in machinery and so forth, the hexagon is 82.7%. The heptagon or septagon, both are used for 7-sided. I use heptagon. Is 87.01%, and we just did the hexagon, or the octagon, I'm sorry, which was 90.04%. So I invite you to practice the pentagon, the hexagon, and the heptagon. See if your figures come out to these on the, that I wrote on the board. And it brings an interesting question. As you get more sides, 10-sided figure, 12-sided figure, we're already at 8-sided, we're at 90%. We'll keep sneaking up on that 100%. If you envision a polygon that has an infinite number of sides, sort of sometimes hard to wrap your head around that, but the limiting case of an ever-expanding polygon family is going to be the circle. The circle is a polygon with an infinite number of sides. Therefore, each of those sides is connecting two infinitely small points, and it gives us the smooth curve, but it all is in the same family, it being the end result of an ever-expanding family of polygons. Hope you enjoyed these calculations. Good practice for using your geometry, your algebra, and your trigonometry. And I wish you the best as you practice your calculations.